Design a can. Example 4, designing a can. Here's what we are told. We want a 1-liter oil can. It is designed as a right circular cylinder. And we want to minimize the material use. So let's analyze this. Useful information, 1-liter oil can. We should know that 1 liter is equal to 1,000 cubic centimeters. If you don't, you do now. File it away in those memory banks. A right circular cylinder, so I'm going to go ahead and skip forward to making a drawing of the situation. Right circular cylinder will have a radius and a height, and minimize the material use. So minimize, critical point again, material use. So a couple interesting things here. First of all, material use means I'm interested in the surface area. And surface area of a right circular cylinder can be found by adding the top and bottom, pi r squared twice, to the can walls, the cylinder walls. Well, the cylinder walls can be found by taking the circumference of the cylinder and multiplying it by the height. So that's what I want to minimize. I want to minimize this. Now, notice that I have 2 variables, r and h, which means I need another equation because I've got 2 things that can change here. Well, 1 liter is a volume, and I know that volume of a right circular cylinder is equal to the area of the base times the height, and I know that in this case this is equal to 1,000, which means that h is equal to 1,000 over pi r squared. Going back to my area equation, I can now rewrite this in terms of a single variable. 2 pi r times 1,000 over pi r squared. Little simplification, the pi's go away, one of the r's goes away, and I'm left with 2 pi r squared plus 2,000 over r. So, minimizing, let's start solving. The derivative of a with respect to r is, well, 4 pi r minus 2,000 over r squared. I'm not sure how I got that. Think about it a little bit. Hint, I rewrote r on the denominator as r to the negative 1 and used the power rule. And I want this equal to 0 to find those critical points. Multiply everything by r squared. I get 4 pi r cubed minus 2,000 equals 0. And solving for r, I get r equals the cube root of 2,000 over 4 pi, which is approximately 5.419 centimeters. Is this a minimum? Well, let's, in this case, do the second derivative test, just because we have it. The second derivative of this function is 4 pi plus 2,000 over r cubed. And the reason I say let's do the second derivative test is because it doesn't actually require us to do any calculations. I could have plugged in some number less than 5, some number greater than 5.419, done those calculations, but let's say I don't have a calculator. Let's say I'm just doing this, so far there's nothing on here that I've needed a calculator for except, well, I take that back. Okay, I had to find the cube root of 2,000 over 4 pi. But just looking at this second derivative, 4 pi is a positive. And since r has to be positive, you can't have a negative radius. That means 2,000 over r cubed must be positive, which means that for all possible values of the radius, this has to be a positive number, which means that this is in fact a minimum value. So what have I got here? I have a radius of 5.419 centimeters. I'm doing a quick calculation of the height of my can by plugging that back into my equation for the height. I get a height of 10.839 centimeters, which means that the least amount of material needed to make a 1 liter can will result when the radius of the can is 5.419 centimeters. The height is 10.839 centimeters. All right. And you may notice that that's sort of, I mean, in terms of right cylinders, 10.839 and a diameter of about 10 point, oh, well, would you look at that? 5.419 doubled, 10.838. In other words, a square. All right, go ahead and do exercise 11, and we'll be back with the next